Hello everyone, I'm going to talk about Chapter 3, Moving Averages and Exponential Smoothing Methods in this video. This chapter introduces models applicable to time series data with seasonal, trend, or both seasonal and trend component and stationary data. Forecasting methods discussed in this chapter can be classified as first, moving average methods, and then second, exponential smoothing methods. In moving average methods, the observations are going to be given an equal weight. I will explain in the following slides what I mean by equal weighted observations. In exponential smoothing methods, we have an unequal set of weights to pass data. All methods in this group require that certain parameters to be defined. I will explain what I mean by certain parameters in the following slides. These parameters, with values between 0 and 1, will determine the unequal weights to be applied to pass data. Let's start with moving average methods. If a time series is generated by a constant process subject to random error, then mean is a useful statistics and can be used as a forecast for the next period. Averaging methods are suitable for stationary time series data. Let's try to understand when we say stationary and randomly determined data. So let's assume that this is our data and this is our time. And then you observe that data set is like this. As you see, the data, it's not following a trend or downward trend. There are no seasonal patterns that you can define in this data. So this kind of data is described by random error. Why it's random error? Because today you might observe a low value, but tomorrow you might observe a high value, and they are not related to each other. And we call this type of data as stationary time series data. If you don't have any trend or seasonal pattern, then the data is called as stationary. So you may think about randomness in the data like a forecast, weather forecast. Let's say today is rainy. And if the data that you observe tomorrow depends on today, then you expect a rainy, at least cloudy weather. But if it's random, then you might have a sunny weather tomorrow. So stationary time series defined by a data set that does not have any trend or any seasonal variation. And averaging the data, averaging this what is observed, is the best forecast for a stationary data. Exponential smoothing methods can be divided into three types. The first one is the simplest exponential smoothing method, which can be called as SES, where only one parameter needs to be estimated. This estimation is good for forecasting stationary data. Stationary. Again, no trend, no seasonal patterns. Holt's method is an extension of simple exponential smoothing, makes use of two different parameters, and allows forecasting for series with trend. So if there is a trend in the data, like this, going up or going down, then Holt's method is a better forecasting technique. Holt-Winters method, again, is an extension of simple exponential smoothing method, involves three smoothing parameters to smooth the data, the trend, and the seasonal index. So if you observe a data like this, both a trend and there is also seasonal patterns, regular patterns that always you observe in the data, then Holt-Winters method is a better forecast. Let's start with moving average methods. This method is appropriate when there is no noticeable trend or seasonality. So we are talking about a stationary data, as I said before. Stationary data, the errors are random. Any observation today does not depend on yesterday or 2 days before. The moving average for time period T is the mean of K most recent observations. So that K can be 3, 5, or 12, or any other number. The constant number K is specified at the outset. Let's say if we are talking about moving average 3, MA3. What we are going to do, let's say we want to forecast quarter 4 sales for 2017. Then I'm going to use three most recent observations, which are quarter 1, quarter 2, and quarter 3 of 2017. I will get average of this data. How I'm going to do that? Quarter 1 plus quarter 2 plus quarter 3 divided by 3. That's going to be the average. And use that average to forecast for quarter 4. If you want to do for 5 periods, which is MA5, what I'm going to do, let's change the color. For MA5, before I have quarter 1, quarter 2, quarter 3 to forecast quarter 4. This was for 2017. Now, if I want to use MA5, then I need to add quarter 4 and quarter 3 from 2016 because I need 5 most recent observation to forecast quarter 4. So what is going to happen? I'm going to get average of quarter 3 from 2016, quarter 4 from 2016, quarter 1, quarter 2, and quarter 3 from 2017 and divide by 5 to find quarter 4 forecast. The constant number k is specified at the outset. As I said, you are going to make a decision which k to use. The smaller the number k, the more weight is given to recent periods. And the greater the number k, the less weight is given to more recent periods. In the simple and moving average models, the forecast value is ft, which is the forecast. In our case, it might be quarter 4, is going to be the sum of the most recent periods divided by the number of periods. So let's see one numerical example. Kroger sells bottled spring water and we have monthly sales data. Now if we want to use moving average 3, we are going to get most recent 3 periods of data. We are going to sum all this data and then divide by 3. This is going to be the forecast for July. If I want to use moving average 5, I'm going to use 5 periods of data. I'm going to sum them up and divide by 5. Here are the solutions. So for moving averages, equal weights are assigned to each observation. As we do the example quarter 1, quarter 2, and quarter 3 dividing by 3, equal weights are given to each past observation. And we forecast quarter 4. And when we have the actual data for quarter 4, actual data, and we want to forecast, let's say 2018 quarter 1, we are going to drop quarter 1, 2017, and use the most recent 3 periods of past data to forecast quarter 1. Each new data point is included in the average as it becomes available, and oldest data point is discarded. The moving average model does not handle trend or seasonality very well. Here is another example. The weekly sales figures in millions of dollars presented in the following table are used by a major department store to determine the need for temporary sales personnel. You have the 25th weeks of data. If you plot the actual sales, you're going to see that there's no trend in the data, and you cannot see any seasonal patterns that are regular deviations or changes in the data set. So given this, the best forecasting method for this type of data is going to be moving average. Let's use a 3-week moving average, K3, for the department store sales to forecast for the week 24 and 26. Here, for week 24, we need to know the actual data for 23, week 23, 22, and 21, and average it out. What we get is 5.9. Since we have an actual data for week 24, we can easily calculate the forecast error. Actual data turns out to be 6 million. So our forecast is 5.9. We make a mistake of $0.1 million of sales. The forecast for week 26 requires the actual data for week 25, 24, and 23. And then we can calculate by summing all these sales data and dividing by 3. 5.7 is our forecast. When we have the actual data, we can calculate our forecast error. Here is the plot of the sales with actual data and the forecast. Forecast is represented by the pink line, and the sales are represented by the blue line. We did a pretty good job with forecasting, and our forecasting error is $0.63 million. Next group of models that we are going to talk today is exponential smoothing methods. The prediction of the future depends mostly on the most recent observation and on the error for the latest forecast. Here, the important thing is to understand the smoothing constant alpha, and it denotes the importance of the past data. This method provides an exponentially weighted moving average of all previously observed values, and again appropriate for the data with no predictable upward or downward trend. So we are talking about, again, stationary data set to apply simple exponential smoothing model. The aim is to estimate the current level and is used as a forecast of future value. Why use exponential smoothing method? Use less storage space for data, extremely accurate, easy to understand, little calculation complexity. There are simple accuracy tests. Let's try to understand the algebraic form of exponential smoothing. Assume that we are currently in period t. We calculated the forecast for the last period t minus 1, and we know that the actual demand or sales data for the last period t minus 1. So our forecast today or for the next period is going to depend on the forecast that we did in the previous period or today plus alpha, a smoothing constant, times the actual data in t minus 1 minus the forecast in t minus 1. So as you see, this is the error we made in t minus 1, the previous period. We are updating our previous period's forecast with some weight, given some weight, to the error that we made in the previous period. That's what exponential smoothing method does. The smoothing constant alpha expresses how much our forecast will react to observed differences. Okay, these are the observed differences. If alpha is low, let's say 0.1, 0.2, there is little reaction to that error, and in alpha is high, there is a lot of reaction to that error. To estimate alpha, we are going to forecast for alpha equal to 0.1, 0.2, 0.3, up to 0.9, and then we check the root mean square error of each forecast. And then the value of the alpha with the smallest root mean square error is chosen for use in producing the future forecasts. So, to start the algorithm, let's write first simple exponential smoothing model the way we learned to forecast for period 2. What we have learned by now in algebraic form, I need the forecast in period 1 plus alpha times the error that I made in period 1. This is the error. And alpha is going to weight to that error. And we are going to update the first period's forecast with that error. If we reorganize this form and opening up the parentheses, I'm just trying to get you to this equation. F2 is equal to F1 plus alpha A1 minus alpha F1. And if you combine all these alpha, F2 forecast in period 2 will be alpha A1 actual data plus 1 minus alpha F1. So this form is equal to this form. There is no difference between them. It's just a different presentation of the same exponential smoothing method. So if you look at this equation, you realize that we need F1, forecast for the first period. For sure we have actual data for first period, but we don't have forecast for the first period. Since F1 is not known, we can set the first estimate equal to the first observation. We will usually follow this one, set the first estimate equal to the first observation, but you can also use the average of the first 5 or 6 observations for the initial smoothed value. Here is another example, University of Michigan Index of Consumer Sentiment, and we need to forecast the data for January 97. Okay, I forecast using alpha 0.6 and alpha 0.3. The pink one is with alpha 0.3 and the green one is with alpha 0.6. As you realize, the smoothing constant with 0.6 gives a smaller root mean square error, so I'm going to choose this model and I'm going to choose this smoothing constant. The next exponential smoothing model is Holt's method. Holt's two-parameter exponential smoothing method is an extension of simple exponential smoothing. It adds a growth factor or trend factor to the smoothing equation as a way of adjusting for the trend. Before exponential smoothing, we said that the data does not have trend. It's a stationary data. There is no upward pattern or there is no seasonal patterns in the data. But sometimes we have trend in the data. Then you need to use the Holt's exponential smoothing method. The data like this, going like up, or a data set like downward trend. Holt's exponential smoothing method provides you lower errors. So in Holt's exponential smoothing method, we have 3 equations and 2 smoothing constants. Forecast for level. When we say forecast for level, that's a forecast without thinking that there is a trend. We first forecast without trend, and then we forecast trend, and then we add trend to our forecast to get the final forecast. This is the idea in Holt's method. You are forecasting level and trend separately, and then you combine both of them to find the final forecast. And the last equation is forecasting the future periods in Holt's method. The weight alpha and beta can be selected subjectively. You can determine the weight, or by minimizing a measure forecast error such as root mean square error. So here, if you want to minimize the error, I highly recommend you to use solver add-in in Excel. In the video, the Excel video, the Winters exponential smoothing method, I show you how to use solver to minimize alpha and beta. But for assignments, I'm going to provide you alpha and beta, and in real life, you can choose your alpha and beta. You don't have to use solver add-in to choose the optimal level for alpha and beta. But just be careful, if you use large weights for alpha and beta, you are assuming that there are more rapid changes in the component. So alpha was used for level forecast and beta is used for trend forecast. So if there is a rapid change in trend, you might think about using a higher beta values. And if there are rapid changes in the level, you might think about using larger weights for alpha. And if it's reverse, then you might choose smaller weights for both of them. Here is an example. This is an Acme tool company's sales. Let's first check the graph of the sales. Here is the year and here is the sales. We observe that there is first a downward trend in the sales, and then after 10 years, you see an upward trend. So this is a non-stationary time series because there is a trend in the data. The second important thing is that there is a seasonal pattern in the data. Always the first quarter sales are higher than any other quarters. So if we use Holt's method to forecast this data by setting alpha 0.3 and beta 0.1, we will get pink line forecast of the sales. So here you realize that our forecast captures the trend, but there is a problem with Holt's method. It's not good at forecasting the seasonal variation in quarter one. Winters exponential smoothing model is the second extension of the basic simple exponential smoothing model. It's used for data that exhibit both trend and seasonality. And it's a 3-parameter, it's not 2-parameter. With simple exponential smoothing, we have only alpha, smoothing constant. With Holt's, we have alpha and beta, one for level, one for trend. And with Winters, we have alpha, beta, and gamma. Alpha is going to be the smoothing constant for level, beta is for trend, and gamma is going to be for seasonality. The 4 equations are necessary for Winters method. The first one is for level forecast, the second one is for trend, and the last one is for seasonality. And the 4th equation is for forecasting future periods, which is not on the slide. So we will apply Winters method to Acme tool company sales. The value for alpha is 0.4, the value for beta is 0.1, and the value for gamma is 0.3. The smoothing constant alpha smooths the data to eliminate randomness. The beta smooths the trend in the data set. Finally, the gamma smooths the seasonality in the data. Alpha is for randomness. Beta is for trend, smoothing the trend. And gamma is for seasonality. 3 parameters, seasonality. And here are the results. We use alpha 0.4, beta 0.1, gamma 0.3, and root mean square error. As you realize, with Holt's method, it was 155.5 with the same data set. With Winters method, it's lower. And when you check the graph, you realize that with Winters, we are forecasting better. Why? Let's see. We have the trend. Yes, we capture the trend. We also capture the seasonality in the data. So it's a better estimate. That's why we have a lower root mean square error. So that completes the chapter. I hope these slides and this lecture will help you to complete your assignment and as well as your midterm test this week.